Hello everyone, welcome back. So today we are going to talk about really old video game graphics, right? So how do old retro video games display graphics on the screen? This all started whenever one of my students asked me, like, Gustavo, I'm learning how to program using OpenGL or DirectX, and I have all these C++ functions, and that's all fine, right? We are using these graphics cards behind the scene, this modern hardware. There are the graphics cards. But how do programmers display graphics in these very old machines? And when I say old machines, I'm actually talking about arcade, right? Those big, bulky machines, arcades, or even the first Atari 2600, NES, things like that, right? The first, second, and third generations of old game consoles. And the main reason that I decided to stop, have mate, right, have a chimarrão and discuss this quickly, is because I noticed that several students, they don't realize that these old machines, right, the really, really old machines in the 70s, they didn't even have a processor, they didn't have cartridges, they didn't have even ROM chips. Right? So that is why I want to explain, so how did we actually get something to be displayed on the screen if we don't have a microprocessor, right? We don't have a CPU in these very, very old arcade machines, like, of course, Pong, right? We have here Pong, and if you look at Pong, I mean, the arcade machine of Pong, right? If you go and you actually open the cabinet of that arcade machine, you will see that it is just a bunch of circuits, right? So you will see that these old machines like Pong or even Breakout, right? These very classic arcade machines from the early 70s, they were designed, they were hardwired in a way that you have the game, the logic of the game, respected the output of this discrete circuit. Right? So you have this circuit design that you have a clock, and as the clock ticks, the circuit outputs signals, right? You go and you have electricity flowing through those circuits designed in a way that the output, every scan line of the CRT display, every line of the monitor that you see, everything is being clocked at precise time to display exactly those scan lines. And if you look at the graphics of Pong, this is a good example for us to show that we don't have control over bitmap pixels of the screen. In this early discrete circuit design that you have of Pong, for example, all you could really do with the signal was, is this signal white or black, right? So is it on or off? That is why everything is basically rectangular, right? So as you go and the beam, right, the CRT beam, the electron beam goes and scans line by line of the television set, you can either say, is this pixel on or is this pixel off? Or is this video signal on or off? Whenever we go, the output of that circuit is going to be either on or off. Got it? And look, there is a resource that I really, really like, which is a complete specification of the Pong arcade machine in JavaScript, but simulating circuits. So here we're going to find a simulation of the 72 Atari arcade Pong game at a circuit level, which means that all these links right here, they are going to tell us the circuit, all the flip-flops, all the logical gates, everything that has to do with the circuit and how everything is connected together in order to, at the end, the signal displayed is the actual Pong game on the television. So to start, we need to have a clock generator. Do you agree? And whenever we have a clock generator, this thing is going to be basically a crystal clock, right? So we have an actual component, right? This is the component that you have, that as you feed current to this crystal, that quartz is going to vibrate at a certain frequency. That is the clock that we can use to have this controlled time step, right? So you have this tick, 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 because time passes. We need to go and generate that game logic. We need to flow electricity through that diagram or circuit in order to generate the output signal, frame per frame, right? So this thing is running frame per frame, and all these circuits are going to work together to generate that final output with the pedals, with the ball, with the net in the middle, right? Look, there is no ROM, there is no cartridge, there is no microprocessor. It's just a circuit, everything connected together in order to generate that final video signal, right? So look here at this clock. This thing, for example, this is the actual clock, right? The little crystal that we have, that quartz crystal. This is the thing that is generating that tick clock, that vibration of the frequency of the clock. And then you have all these circuits that you have a resistor here, you have this inverter, right, this NOT gate, you have everything connected, you have this JK flip-flop, and then you have a clock output right here. And this is, of course, the output, right? You have pulse up and pulse down at a certain frequency, right? Several times per second. This is going to be the frequency. This is going to be how many cycles that clock is running. We can actually, well, increase or decrease the simulation speed if we want. But if we go now to the next one, which is drawing the net, using this clock, we can now go to the next set of diagrams, a discrete circuit, right? There is no microprocessor. Everything is designed at this circuit level. You have all this inverted, you have the clock here being fed, the horizontal counter. So everything that is being displayed right here, the vertical counter, you have all the circuits that are being printed in the board, of course, right? You have everything connected together. And this simulation right here on the right, this is the net, right? So as you have vertical counter, you count things precisely to say on or off, on or off. And as the scan lines are being drawn, this red line right here is the actual CRT, right? The electron beam scanning things from left to right, top to bottom. This is us drawing the net. And then if you go right after you have all this net right here, let's just look at the pedal position circuit. So the circuits are going to become more complex, and you have different types of components. Here is a NAND gate, right? AND with a NOT. You have other types of R flip-flops, inverters, resistors. So everything is discrete circuits. Do you see where we're going with this? So this is an amazing, amazing resource. I actually tell my students to go and take a look at this circuit level Pong simulation. You can run it in your browser, you can see the output, you can actually specify what is going on. So this, for example, this NAND gate that has 4 inputs, you can actually double click and see what is going on. You have the number of inputs, what is the output high voltage. You can go and granularly see what is the input, the output, and understand the logic that is being designed by that circuit, right? Discrete circuit. There is no microprocessor here, there is no ROM, there is no cartridge. Everything is basically almost like hand-wired in this board. If you open the cabinet of Pong, you are going to see the circuits being either internally designed or some integrated circuits that you have inside the cabinet. And everything at the end means, what is the output signal for the CRT, for the display? Is this thing white or black, right? Is this on or off? And that is why we have these very rectangular outputs, right? You have the net, everything is just on or off. Right here, to generate this thing, it is either on or off. So the video signal is either active or not. That is why we can generate this rectangular image. So as the scan lines are passing, we're going to go and generate that thing or not. Got it? And look, we have actually other examples here, right? The simulator that I showed here, if you look at the index, you have how to draw the pedals. So you have a circuit, you have a set of components that know how to draw the pedal. So everything together, you see, the pedals are being drawn right here. I can actually change with the controller where the first pedal is being drawn. So you see, as the scan line passes, it's right here. If I go up, a little bit up. So this red line is the scan lines being drawn. As I reach here, it draws the pedal at that specific position. And all the circuits right here are accomplishing that, right? So everything builds on top of what you had before. You have the clock being outputted, you have the horizontal counter for the net, and then you have displaying the net, and then you have the circuit for the pedals, right? So where do we display the pedals? Everything is being done using discrete circuits, right? So this is why we spend so much time learning about these things, right? If you're taking CS classes in college, that is why you probably have this introduction to the computer architecture, right? Where you learn about flip-flops, you learn about logical gates, you learn about all these ideas of accumulators, counters, timers, all these very fundamental building blocks. This is where it all started, right? So that is how we can achieve this discrete circuit design. And this is a great resource. I love showing this simulation at discrete circuit level of the Pong arcade machine. And of course, if you go to the index, you're going to have at the end, everything builds up until the game logic, serve time. So you have all this logic, the game logic that will perform the pedals moving, the ball bouncing, right? So if you look here at the game logic, and then if you look at serve time, score, miss sound, and then hit sound, you have all these different circuits accomplishing what we want, all right? Look, if you want something more formal, you have a link to the full schematics of all the circuits and how everything connects together right here. So this is a PDF document. It's up to you, right? If you want to understand how Pong was actually designed at circuit level using discrete circuits, this is a great resource. So I hope it clarifies a little bit how we achieve this very, very rudimentary graphics only by saying video output on, video output off, and then having all these discrete circuits controlling the logic of what is on or off in our display. Got it? So this was Pong, right? So very rudimentary graphics, only kind of basically just sparks on metal, right? Just saying on or off, displaying scan lines, video signal on or off, rectangular blocky graphics. There was a game called Highway, which is basically a game where you have a road in the background moving to the right and left, and then you have to control this car. One technique that I want to point out with this game right here, the way that it generated this effect of going left and right with the car is basically by distorting the graphics. So when I say distorting the graphics, it goes and distorts the video signal, right? So to simulate this rotation of the car to the left or to the right, you go and you distort. It's almost like you go and you skew the signal, right? And how do you achieve that? Well, how this machine achieves that is basically by delaying the display of the scan line, one scan line per scan line. So if I want to go and I want to rotate to the left, I have to go and as I'm displaying, as the CRT is displaying the game information, as I reach the top part of the car, I draw the pixels that I have to draw, and then for the next scan line, the circuit delays the video signal. So the pixels are going to be delayed in each scan line, so you're going to have this distorted image. Look, it's weird because this is not rotation, right? We are not rotating that bitmap. We are skewing, right? So we are distorting things. We are distorting the raw video signal. Got it? So again, it's very weird. You have this very clear distortion going on in the video signal, but that is what they managed to do, right? Everything was basically just being outputted using discrete circuits in this case. But there are some actual interesting things that people did. If you look at also another game, right? I think it was 1976, a game called Breakout, famous as well. But do you see how Breakout, you can actually have these options of colors on top. Yes, some machines, they could display colors, but for most machines of this time, it was very expensive to display color information as well. So something super inventive that people did was, instead of changing the pixels and displaying these expensive color pixels, what you had was, you either had kind of this cellophane layer on top of the display, or even a tinted glass on top. So the pixels underneath are either on or off, right? Just white or black. But you could have either glass or a cellophane overlay on top of the screen. So do you see how you have this very segmented, these divisions of colors? This is red, this is yellow, this is green, this is yellow, and then right here you have a set of scan lines that are all blue. You could achieve that by not changing the color of the pixels inside. So you don't actually use the CRT to display different colors, but you just use this kind of overlay, either a tinted glass that is painted red, the glass is painted yellow, the glass is painted green, all these segmented lines, or you have a cellophane overlay. And not just arcade machines, But if you look, for example, at, well, look at this example right here, right? The Magnavox Odyssey. This is arguably the first home game console that was ever out there, right? So this is probably the official first home game console. This was for the first generation of home game consoles. And the Magnavox Odyssey also, all it could actually draw on the screen was basically a net and then two rectangles, if I'm not mistaken, moving around, right? So the rectangles could move around with the controller. A net and two rectangles, they're just white blocks. It is not very interesting to only move the rectangles around the screen. So what gamers used to do with Magnavox Odyssey is, you could buy these overlays, right? So you have this kind of sheet overlay that you could just go and you could cling, right? With static, you could cling on the television monitor, on the display. So by having this overlay on top, this overlay had colors, and the overlay had obstacles, and the overlay have this extra information that kind of made sense with the rectangles in the background, right? So what the CRT display used to draw was only on or off signals, right? It's just those two rectangles and the net. But then if you have that overlay, right, that physical overlay sheet on top of the monitor, then you have now obstacles, you have maybe a labyrinth, you have extra graphical information that is not being displayed by the monitor, but you basically have this physical presence of a graphics on top of that thing. I think it's quite inventive, right, to kind of mix and have this hack of mixing physical objects, this kind of overlay that you can just go and cling with static on the monitor, and then you just have those rectangles moving behind these overlays. I thought it was very inventive whenever I saw the Odyssey before. So this was the Magnavox Odyssey. Super famous, again, the first official home console, right? Probably the one that kickstarted the whole, all the generations of home consoles. This is the first generation. Right, but we need more, right? So as time evolved and as hardware evolved as well, we could not only rely on things like video signal on or off. What happened was, we wanted to get more graphics information. And when I say graphics information, it's probably things like better pixel control of what can be drawn or not. So not just rectangles on the screen, I want to be able to draw a little character, right? So maybe Mario, right? Very blocky pixel graphics Mario. Maybe I want to display color information. So for us to have this granular control of the pixels and the bitmap pattern of all these graphics, then we are going now to move to the second generation by storing graphics information somewhere in memory, right? So you're going to have all these bit patterns, right? So what is on or off, you save these things in memory, usually ROM memory, right? ROM memory is basically a chip that is read-only memory. So you go, you program that chip, and inside that chip you have this addressable memory with information of what is on or off. If you think about ROM, you have all these addressable memory positions, right? So whenever you have ROM, this read-only memory, you have to address those things, right? Everything has an address. So you have a certain address in ROM, and then if you want to display this bitmap pattern, for example, you could just go and fetch from ROM, right? So you do not need to rely on a discrete circuit to display all the logic to generate this on or off. You can just go and use the circuits to fetch and read from ROM what is on or off. So you just go, you read all these positions from 8001 until 8009, right? Hexadecimal, of course. And then you just go and you translate this into pixel on, pixel off, right? Or whatever graphics detail that you have, right? Bitmap on or off, and then you achieve the pattern that you want to display in the monitor. Oh, and before ROM, you might think, okay, Gustavo, so if we didn't have ROM before to encode and store that bitmap pattern, how did early games manage to display this more elaborate pixel art, right? This bitmap pattern arts in the games? Well, one example of something super interesting is the game Space Race. So if you look at the game Space Race, do you see how you have this kind of sprite-like bitmap pattern of the spaceship? the way that they achieve that without using ROM to encode that bitmap pattern is, in the circuit, you have this matrix of diodes. And you can see here on the right, I am already showing a picture of the actual circuit. And all those diodes right there, they are outputting 1 or 0, depending on how they are connected to that circuit. Do you see? It's almost like I have this diode-based pixel art. That right there is the left part of the spaceship. Do you agree with me? And then, of course, since you have the left part of the spaceship, then it is just a matter of going and mirroring that signal. You go and you duplicate and you mirror, you flip that signal to get the other half of the spaceship. Super cool, right? So this was a pre-ROM era, right? Whenever you have to hardwire this diode matrix with all the pixels and the bitmap pattern that you want. But then, of course, whenever we enter the ROM era, then you have all this luxury of having addressable memory, and you can store in ROM, in this memory chip, the bitmap pattern that you want. Got it? Look, still no CPU, still no microprocessor, right? And then the big divisor is the fact that whenever we started using this microprocessor, this core chips that knew how to compute super fast, they ran operations, they can store things into registers, so then we enter the era of the microprocessor, right? And look, the microprocessor is this computer component where all the logic, all the data, all the control is included in one integrated circuit. A unique chip that is clock-driven, register-based, digital integrated circuit. It usually works with binary data, right? So whenever you have a CPU, this thing right here is clock-driven because everything, as we tick the clock, things happen inside the processor, right? The processor performs operations, right? Instructions. You have an instruction set, and you usually have things like an ALU, an arithmetic logic unit, to perform things like adding two values together, subtracting values together, comparing if things are equal, less than, greater than. So this is the responsibility of the ALU, and the ALU resides inside the CPU, usually. And then the CPU has registers inside for us to perform computations with the registers and other types of data. So this was a super huge game changer, right? So this is exactly what we need to look right now, because as you introduce these ideas of having an integrated circuit that knows how to add values, subtract values super fast, right, with this high frequency, right? You have megahertz, you have all these ideas of several times per second these computations happening, and the CPU, super important, the CPU orchestrates everything. Because you have connected, usually, right, the CPU can go and fetch values from a read-only memory. The CPU can go and move bits from and to RAM as well to store values. So the CPU is what orchestrates everything. And look, let's just go ahead and think about like moving from the first generation to the second generation. And when I say second generation, this thing right here, I'm looking at, let's say, the Atari 2600 console, right? Which uses exactly this type of components. The Atari 2600, or the Atari VCS, as most people call it, the Atari 2600 had a CPU inside, which was the MOS 6502, super famous CPU. The CPU knows how to add values, subtract values. It has 3 registers. It knows how to compare values if it is equals to 0, different than 0. So the 6502 CPU of the Atari 2600 has an ALU inside. It has RAM memory. So we have a little bit of RAM that we can store values and read values, right? So we have a place to store information. And look, super important. Do you see that ROM right there? That ROM, as we enter the second generation of home game consoles, that ROM right there became usually part of the game cartridge. So that thing right there, as you have your game cartridge, you have a ROM chip, and that ROM chip has inside the actual instructions for the game logic. So you go, you get the cartridge, you slide in the little cartridge slot, and then the CPU has direct access to that ROM. It can go and read instructions to be executed by the game. So the actual game logic, the game graphics data, all those bitmap patterns, they are all stored in ROM per game. Do you see how this is important? Because if everything now, this ROM, comes in the cartridge, that means that we moved from having one game per machine, so we don't have one game per console anymore. We have now one console, and we can play multiple games just by having these multiple cartridges, right? All these game packs. So you have one console, which is the Atari 2600, let's say, one console, and then you have multiple games. Because you separate, you delegate the game logic and graphics to the cartridge, and the ROM is being accessed in that place right there. Got it? So this is a super game changer again, right? Exactly, literally a game changer, because you have the Atari 2600 that has a CPU inside, the 6502 CPU. It has RAM inside. You have 128 bytes of RAM. Let me say this again. 128 bytes of RAM. This is all the Atari 2600 had, 128 bytes of RAM memory, but you have the ROM chip with the game logic, all the processor instructions to know how to jump, move, and everything is connected in the cartridge, right? So you go, you slide the cartridge in the slot, and then the CPU has direct access to that ROM, to that game information. And of course, when we talk about the architecture of the 2600, right, in the second generation of game consoles, you have other things connected here as well. So you might have connected to the bus of the architecture, you might have things like controller, right? So you're going to have controller input, you're going to have some controller ports that you can go and poke, and they are mapped into memory. You have a special graphics chip. In the case of the 2600, this graphics chip is called the TIA, the Television Interface Adapter. So this graphics chip, this is what knows how to go and send video signals to the CRT monitor. The TIA chip, in the case of the 2600, it was super interesting because the 2600 did not have a frame buffer. And when I say frame buffer, it means that we don't have a map in memory of what is being displayed on the screen, right? So we don't have memory enough to save all the pixels with all the colors of what is being displayed on the screen. So we don't have this map, right, in memory to what is being displayed. So what happens with the 2600 is you will see people say that we were always racing the beam, right? So we have the electron beam, and we were always racing the beam from top to bottom, left to right. So we have to, in the case of the 2600, we have to time everything precisely in order to go, and as the beam is moving, we go and we render something in red, and then we render something in yellow, next line, right? You will see that we talk about lines of scan, right? So as we are scanning the lines of the CRT display, of this raster, we go and then one scan line, you have to go and program to display certain colors. Next scan line, you have to program everything again to display the next scan line. So we are always racing the beam, timing everything precisely in order to go and change the graphics objects that you see on your display. It was a super fun time, right? So it was a little bit hard to program, but you have complete control of what is going on in your frame, right? The graphics frame that you have, picture per picture frame, 60 frames per second, let's say you have, and you have this refresh rate of the monitor, right? You have to control everything frame per frame, what is being displayed, and all you had was a CPU, a very limited but useful CPU with an ALU, with registers. You have RAM, 128 bytes of RAM, and you have ROM, right? So you have this 4 kilobytes of instructions in ROM that you could use to store game logic, you could use to store bitmap information. Remember the sprites with those ones or zeros to what is being displayed or not, right? Pixel on or pixel off. So this is the Atari 2600 era, the second generation of home game consoles, right? And look, I am aware that YouTube is not a proper education platform, right? We are just here to have a conversation while I have my mate, right? While I have my chimarrão. But if you really want to learn how to program for something like the Atari 2600, I would suggest maybe, I do have lectures where I teach how to go and program assembly using 6502 assembly and how to program for the 2600, right? So if that is something that you think you would like and you will enjoy learning the low-level details of how these Atari 2600 games are being developed, I would just leave a link down here in the description so you can just go ahead and look at those lectures yourself, right? Then you really learn how to program for the Atari 2600 using assembly language, which I think every computer science student should do at least once in their life, right? You really learn a lot about computer architecture, digital machine design. It is a great set of lectures I think everyone should enjoy. So this was the second generation of home game console, right? We need to start thinking about evolving with time. How do we push more and more pixels on the screen with more color, more resolution? How do we evolve graphics going now from the second generation with the Atari 2600 to the third generation with the NES or the Sega Master System, right? So we have these different consoles. I am going to focus on the Nintendo Entertainment System, the NES, because I think there are several components and the way that the NES draw things on the screen. There is one thing in particular that I think is going to be super useful for us to look at. So, as always, everything starts with the arcade, right? In this time period, everything started early in the arcade machines. And then we try to go and replicate the arcade experience into people's homes. That is the whole deal, right? Everything starts in the arcade, people go and they spend their money buying coins, and then as that game becomes popular, they try to go and replicate and bring that arcade experience into people's homes. This was kind of what happened as well with the whole third generation of game consoles. So, Nintendo, this company from Japan, they were quite successful developing these arcade games, and one of the games that they were developing and that got some traction was Donkey Kong, right? So Donkey Kong, you have this arcade machine right here, and it had some inventive technologies because it used something tile-based. Everything that you see right here, all the pixels that you see displaying right here, they are controlled by tile map information. Right, so you group pixels in tiles, and then you have a source of truth, right? The source of truth is this table of tiles, and then you paint the canvas with those tiles. Do you see where we're going? So it is not pixel per pixel information. We don't store this huge amount of pixels one by one. You have a tile map, and then for you to go and draw the information on the screen, you go and you fetch that information from the tiles. Right? So in tile information, by grouping everything in this kind of 8 by 8 pixels, you can compress that data and store more information in less bytes. Right? That is the whole game. These ideas of tile-based graphics, it is not just something that video game consoles used. Think, for example, if you ever used this kind of terminal-based text mode MS-DOS, or even a Linux terminal, right? From the old school terminal-based text mode video mode, right? So do you remember how if you kind of went there and you turn your 486 computer or your Pentium computer on, you enter this text mode, which was basically you have all these ASCII characters, the glyphs, that is also tile map based, right? Because you have in the computer, you have a map of all these ASCII glyphs, right? So you have, for example, the VGA glyphs for the ASCII characters, right? So we have the VGA glyph for the letter A, B, C, D, E, uppercase, and then A, B, C, D, E, lowercase. So all these characters, they were tiles, basically, right? So all these little tiles, you went there, and then whenever we are drawing things on the display, whenever I say CD to change a directory or LS to list files, all those things are being fetched from this ASCII table of tiles. You have all the characters, but everything is being pointed to that table of character, right? That ROM that has all these glyphs, all the actually ASCII drawings of the letters. So this is basically tile-based graphics, but in the context, of course, of computer, right? Home computers and all these reference. But I think it's important for us to have this relationship between tile-based graphics that we were talking about on the NES, and also it is tile-based graphics because you have this text mode, which is just pointing to this ASCII glyphs, right? These letters of ASCII that you can go and display on your terminal. And of course, old school terminals, they were 80 columns by 25 rows, right? So you have this 80 by 25, that was the maximum number of glyphs that you could display in your terminal, right? Your computer terminal. But that was way back then. I just wanted to create this relationship because I also think it's important for students to understand how these two things are connected to each other in a way. So Nintendo, a company from Japan, was having some success with Donkey Kong in the arcade world, but they wanted to start developing a home game console. But that was an issue because in the North American market, the word video game around the early 80s was problematic. No one wanted to talk about video games in America anymore. Why is that? Well, remember the Atari 2600, where you have a ROM and that ROM was in the cartridge? That meant that it was very easy for people to go, generate and write a ROM chip and start distributing Atari 2600 games. So since it was pretty easy for programmers to just go and start creating their own games, you saw a lot of badly written, non-polished, bad quality games for the Atari 2600. So the market being flooded with bad quality games, we had what we call the video game crash, right? People started to really lose their faith in terms of a video game, especially for the home console. That is why it was so hard for Nintendo, right around 1984, 85, to introduce this new home game console in the American market. But after a lot of marketing gimmicks and after a lot of pressure and after a lot of celebrity marketing stunts, they were actually able to get some success. And following the success of the whole Donkey Kong, this new console was the NES. Right? So the Nintendo Entertainment System, the NES, it was largely based on another console called the Famicom that was introduced in Japan before. So the NES was basically an American version of the Japanese Famicom. But of course, if you look at the design, the NES was a lot more modern, with a lot more straight edges, this metallic look, because after all, it was an entertainment system, right? It was not just any video game. Right? Since no one wanted to have anything to do with video games anymore, Nintendo decided to have this. You see how it looks a lot like this VCR player? It is not a video game as we knew how the Atari 2600 was. It is this very modern VCR player looking entertainment system. Got it? So let's just go back here at this idea of the Donkey Kong being tile-based game, right? And how do we translate these ideas of having this tile-based graphics into the NES now? Well, that is exactly what we're going to do. We are going to have in ROM, right? We're going to have into this read-only memory, we're going to have table of tiles. And these tiles are basically groups of this 8 by 8 pixel bitmap information. And this thing right here, this is going to be almost like the brush that we can select, and then we pick the tile, and then we can go and paint the canvas, right? You can think about this as the screen that is going to be displayed. You select the tile, and then you paint the canvas with those tiles. So by having just those two tables of tiles, right, this tile map information, these things are going to be compressed and encoded in ROM, and then you can just go and select the tiles that you go and you display in the screen. That is how you manage to go and work around the limitations of memory size, right? You cannot, again, you cannot waste memory by storing every pixel configuration that you have being displayed on the screen. So what you do is you just store the tile number that you're displaying and maybe some color information, but that is a lot shorter, there's a lot smaller memory footprint than storing all the pixels, right? And this is the whole idea behind tile-based graphics, right? Which is what the NES uses, which is also what the Sega Master System was using in this third generation of home game consoles. Got it? And super interesting, right? How do we divide these things, right? So this thing is the screen, right? What is being displayed on the screen? Where is this table of tiles stored? Well, we are going to store that in the cartridge, right? So this is an NES cartridge. These two tables, you will see that in the NES terminology, we call this pattern tables. So the pattern tables are just this source of tiles that you have inside the cartridge in something called character ROM. So you have a chip that stores all this pixel information, this tiles information. And then the pattern table we are going to use is almost like this is the brush that we paint the canvas, right? And the canvas, the screen that we're going to be displaying in the screen, this is what we call the name table. And the name table is stored in another chip called VRAM, right? The video RAM. So the NES has a video RAM chip that is 2 kilobytes in size. So we have 2 kilobytes of information that we can populate based on those pattern tables. So we use the tiles from the pattern table in the cartridge to go and paint the name table of our VRAM, right? This is what the NES does. And even more importantly, now that we have information coming from the cartridge, right? The tile, the source of the tiles come from the cartridge of the character ROM, and then you have in VRAM, you have the populated name table with what you want to display. How are these things being displayed on the monitor? Well, that is where we have something called the PPU. The PPU is the Picture Processing Unit chip of the NES, and the Picture Processing Unit is the chip responsible for sending the correct signals to the television set to display the scan lines from top to bottom, left to right, right? So you have all those scan lines. The PPU is the one responsible for generating the signals of our CRT display. And that can be either NTSC format or PAL format, depending if you are in the United States or Japan or Europe. So different television formats, you have different PPU chips generating different types of signal. But at the end of the day, the PPU is the one responsible for going and sending those signals to draw that information from the name table to the screen. And not only that, you actually have some options of drawing sprites on top of this name table. So if you want to actually draw the sprite of Mario or the sprite of Goomba, all these sprites are also extra information that you can store in RAM as well. But then again, it's the responsibility of the PPU to combine all these graphics together, all these styles together, and send the correct signals to be displayed to the video output to generate scan line per scan line of our output signal. Good stuff? So look, the idea that you have a microprocessor orchestrating all these things still holds true, right? The NES has this 6502-ish processor as well that goes and knows how to fetch information, have the game logic running. So the 6502 is still the conductor that makes everything happen, right? So in the game cartridge, you have graphics information in form of these two pattern tables for background and sprites, right? One pattern table will be used for background and the other pattern table will be used for sprites on top of the background. But regardless of which pattern table comes background or sprites, you're going to have two pattern tables that is going to be in the character ROM chip, but also we have another chip in the ROM, which is program ROM. And program ROM is exactly what the name says. Program logic, right? So game logic. How fast Mario moves, how high Mario jumps, how many lives do we have, and when is game over. All these processor instructions are inside a chip called program ROM. You have a chip which is character ROM, which comes with the pattern tables, and you have another chip which is program ROM, which comes with the actual game logic processor instructions that we're going to execute to make things move and make the game fun, right? Right, so Gustavo, we are entering, well, we are kind of leaving the third generation, right? So we started with Pong and Breakout and all those Magnavox Odyssey, which was basically just circuits, right? Discrete circuits that had logic and outputted a video signal. And then we started thinking about using ROM chips to encode addressable memory that you can just go and fetch and read information, right? 1 or 0 for bitmap patterns or other things. So ROM was a super important move. And then after ROM, we enter the second generation with cartridges, right? So you have cartridges that had ROM inside, but also a microprocessor coordinating everything and performing all these fast computations to make things move on the screen. And then we left the second generation and we went to the third generation, which I zoomed in on how the NES encodes and display graphics, right? With the PPU, with the idea of having pattern tables, everything is tile-based. And before I go, I just want to mention that, remember how we had the game crash of 1983 with all those bad quality games for the Atari 2600? The way that Nintendo kind of fixed that was by including a little chip inside the NES and another chip inside the cartridge. And the only way that the NES could run that game was if the output generated by that chip, the algorithm output number from the cartridge matched the number from the console. So you have this key lock logic where you could only run a game if the number computation from the chip inside the cartridge matched the chip inside the console. That means quality control. Nintendo could now dictate which games were official NES games. And only the games that had the Nintendo seal of approval would be able to go to the market, being sold, and enter people's homes. So this kind of covers the first, second, and third generation of game consoles that I wanted to cover with this video, but also a couple of really early 70s arcade machines and some special different graphics that were being used so far. Remember, you have those ideas of delaying the signal to distort left and right. We look at these tile-based maps now that you have for Donkey Kong and other games for this third generation. This is how people managed to squeeze everything they could using the limited memory that you have, and kind of always reducing the footprint of memory that we have, because we basically don't have enough memory in ROM and we don't have enough processing power in the processors that we have, right? For example, the processors that we used back then were mostly the 6502 was very famous, right? Especially for the NES and the Atari 2600. But when it came to arcade machines, especially Japanese market arcade machines, another very famous processor was the Zilog Z80. You will see that the Z80 was also a staple. All these old arcade machines, including Donkey Kong arcade machine, ran on a Z80 processor as well. So these two processors, they were very famous in this area, but they were limited, right? The 6502, you have this kind of 1 point something megahertz. That is all the processing power that you had with the 6502 running on the Atari 2600, and also this kind of Recall 6502 processor that was running on, that was inside the Nintendo Entertainment System as well. Super cool mention that I just want to also point out is, do you see how we are talking mostly about pixels, right? And all this, what we call raster graphics. Whenever we talk about these ideas, whenever you see the expression raster graphics, is these ideas that we have the scan lines, the CRT beam, scanning all the lines from left to right, right top to bottom, line by line, rendering the pixels on the display. This is raster graphics. We have this raster of pixels, and then the CRT displays go top to bottom, rendering all these scan lines one by one. Raster graphics. But there was one technique that tried to ease a little bit of the CPU, which was these ideas of vector graphics, right? So vector graphics, as you can see right here, the output is a little bit different because it's mostly based on dots and lines connecting those dots. So the screen, whenever we are displaying this vector graphics, it doesn't scan all the lines from top to bottom, left to right. It just goes and draw these lines connecting those dots in the screen. And this type of technique for some types of games was actually a little bit easier on the CPU, right? The whole problem is that you are basically just displaying the outline of the objects. But as you probably know, games like Asteroids, it was a very classic and traditional way of generating the asteroids graphics in the display. And also, if you ever heard of a machine called the Vectrex, basically the same idea. Vector graphics, but then in this kind of home console machine. Super, super interesting, right? These ideas of having vector graphics. It is a completely different way of thinking about displaying objects instead of this raster-based scan line per scan line filling pixels of the raster. You go and now you have a dot, another dot, and then you just draw this kind of line. And you have this very modern looking Electron type of game, right? Wherever you have these outlines, very, very classic graphics, modern look, but it was not that popular. And as you can see from the third generation, which was this kind of tile-based games, we kind of went back to the raster way of displaying graphics. So you actually don't see many machines using vector graphics. Everything is basically raster graphics from the third generation, fourth generation, and so forth. So this is what I wanted to cover from the first, second, third generation, and a little bit of arcade machines as well, with these different ways of generating graphics in these very, very early video game machines, right? Discrete circuits, and then you have these ideas of diode matrices, remember, where you have diodes generating the sprite pattern, and then ROMs, and then microprocessor, and then you have this second generation, and then tile-based graphics. This is, I think, super important information. Look, I think the next discussion in a different video, I'm basically just finishing my mate now, maybe entering the fourth generation, right? So what is the leap that happened in the fourth generation, which is basically the Super NES and also the Mega Drive, or the Sega Genesis, as it is called in America. So these machines right here, 16 bits, right? You will see that people talk about the 16-bit revolution. This is us entering the fourth generation of home game consoles. Of course, 16 bits and a lot more memory means higher resolution of games, faster games, more granular control, powerful microprocessor, right? So instead of using just 6502, you have a Motorola 68000. So you have this different instruction set, more resolution, more graphics power, a lot more, even music is a lot better, right? So, but thinking about graphics, you have a lot more going on in the fourth generation with these 16-bit machines, right? So let me know in the comments if you want me to cover the 16-bit kind of generation of console, right? The Super NES, the Mega Drive, the Sega Genesis. I think it is going to be a super cool conversation as well, right? I'm going to try to keep these things now as a conversation, just us kind of going over and having this ping-ponging these ideas, right? So let me know if you think this is useful. Let me know if you want to cover the fourth generation. And also, right, after we start talking about this, then we start entering maybe the 3D era, right? We have also the 32-bit machines like the PlayStation with 3D polygons and stuff. There's a lot more going on in graphics as we evolve with time, right? So I think that was what I wanted to cover from today. As always, right? If you want to really understand the low-level programmability of these machines, if you want to program for these machines, just take a look at my lectures. I cover Atari 2600, I teach how to program for the NES, so I'm just going to add the links in the bottom. Just go there and check. We have the super cool lectures on these retro video game consoles, right? And of course, it is not about creating a fun game, but it's about understanding the low level, right? The computer architecture, all these fundamental building blocks that I think every computer science student should learn, regardless if they're going to actually publish a game for the NES or the Atari 2600 in the future. And as always, don't forget to subscribe to receive more information about our future videos. See you soon.